Hello class, welcome to this week's content. Week 4, we're going to cover Chapter 5, IP configuration. This is where we get into the deep topic of subnetting. Alright, so in IP addresses, covered in section 5.1.1 and in other areas of the chapter, you'll find that you really do need to know how to convert binary into decimal. That's an important skill to have, not only for networking, but also for taking the Network Plus exam. Unfortunately, you'll have to know how to do that on paper or in your head. And it may seem kind of daunting, but in reality, the more you work with it, the easier it gets. So don't stress about it. Don't stress about the whole math concept. It's really just place value, and we'll cover that in a little bit. They covered classful addresses, IPv4 addresses. So IPv4, Internet Protocol version 4, has 5 different address ranges, and the last 2 really you'll never use. One, the D range, is for broadcast, and or multicast, and the E range is mostly for government work. So you'll very seldom have any doing with those 2 IP ranges, and you can't alter them anyway. So A, B, and C are the ones that you will most have interaction with. And the A range goes from 1.0.0.0 all the way up to 126.255.255.255. Really, we're only going to cover the first octet because, knowing the rest of the octets is not going to help you at this moment. So, but knowing the Class A range is 1 through 126, Class B range is 128 through 191, the Class C is 192 through 223, and then of course the D ranges and E range. So you will need to remember at least the A through C ranges to pass the Network Plus exam. Unfortunately, a lot of this does require memorization, and if you don't use it all the time, you do tend to forget it, but it's just something that you have to memorize and refresh yourself on. So there are private IP ranges, and we talked before about public versus private. Public IP ranges are usually assigned to websites and forward-facing devices. So businesses that are connected to the network, to the internet, usually have a forward-facing, at least one forward-facing IP address. That means they will be accessible from the internet. So a good example of this is if you have Site A and Site B, just like in your semester assignment. Site A and Site B, they need to share resources, they need to interact with each other's internal or private network, and to do so, they need to connect either via a fiber line that connects the two, or the cheaper route, which is to go over the internet via a tunnel, and we'll talk more about that later. So private IP addresses reside on the internal network. Public IP addresses reside on the public network. They're accessible from the public range, and internal addresses are not. They can't be accessed without that tunneling, and again, we'll cover that later. And so some private IP address ranges for that internal network are reserved in the Class A. The whole 10 range is reserved for internal or private IP addresses. In the B class, the 172.16.00 all the way up to 172.31.255.255 is reserved. Class C, and you'll see this on a lot of home routers, the 192.168.0.0 all the way up to 192.168.255.255. You will have to remember those also for the Network Plus exam. Class A and Class C are actually really easy to remember. I sometimes stumble over Class B because it's just one that nobody ever uses, but you still have to remember it. And subnet masks, you'll also have to remember these. They correlate to the classes of IP addresses. So Class A is an 8-bit subnet, and we'll cover what that means in a bit. The 8-bit subnet, it's 255.0.0.0. Class B is a 16-bit subnet, that's 255.255.0.0. And then the Class C, which is a 24-bit subnet, that's what the / number means, that's a CIDR notation. The Class C is 255.255.255.0. Again, you'll need to remember those for the Network Plus exam. those correlate to the classes of IP address ranges. So at this point, I remember my brain being like just totally frazzled by all the numbers. And what is, a subnet versus subnet mask versus an IP address, and how the two correlate, and then you get into subnetting and your whole world just kind of turns upside down. So subnets let a network device know that this IP address resides on a specific network. It's kind of like, in a sense, almost a zip code, if you can think of it that way. Because the IP address, if you remember, and we'll cover this in a little bit too, is split up into different segments that designate what it is and where it resides. So if you can separate the two, subnet mask and IP address, a little bit, just so you know, one is like a zip code, the other is like an address. They correlate in that they influence each other, but the numbers don't equal the numbers on the other side. So in other words, the bits and so forth, the 255.0.0.0 is not going to change any of the numbers on the 10 range. It's not going to say, 10.2.3.10 means 255.this.that. That's not how it works. So separate the two in your mind in regards to that. The subnet mask is there for the node devices to know network addressing. The IP address is the logical identification number or address of a device. So that's how you would kind of separate the two. They do work together, but separate the two. So network host and broadcast addresses. Get into that real quick. The network portion of the IP address means that is the street it resides on. That was a good example that they gave. The host is the house number. Your broadcast address is as if you were driving down the street and you needed to shout out to everybody who lived there for a specific person for a specific reason. So that's what a broadcast would be, and we'll get into broadcasting and so forth later. But those are the three sections of an IP address that are influenced by the subnet mask. Then you have your special addresses within the various classes, and those special addresses are the 127 range, which that whole range is dedicated to loopback. So if you need to test a NIC, you could open up command prompt and do a ping of 127.0.0.1, and what that does is it sends a packet to your NIC on your computer and waits for a response. And so it's basically like going, am I okay? Yep, I'm okay. That's basically what a loopback does. And so when you ping that address, it responds with, it's received the packets and it had a response. So that's a troubleshooting method that some will use to check their NIC to make sure it's working okay. Don't ask me why they had to designate that entire range to loopback. Nobody seems to be able to answer that clearly. But just remember, the 127 range is completely dedicated to loopback. And if you were to type in, it doesn't matter what loopback address you type in, it's still going to query your NIC. So the other special address is the APIPA, and they covered that in this chapter as well. The 169.254.0.0 to 169.254.255.255. That's for if your computer or device loses contact with DHCP, Windows steps in and says, okay, here's an internal temporary address so you can all be connected together. All right, this is where we get into subnetting, the VLSM, the variable length subnet mask. This, again, the subnetting is confusing to some people, but just remember the subnet helps the node figure out what network the device is on. So you need to know your binary place value in order to do this, and then you'll take a classful subnet and you'll alter it with subnetting to break up that IP range, and I'll explain all of that in just a second. I've listed two calculators here, and you can go online and play with there are myriads of calculators, but these two specific ones show you different information, kind of helpful. All right, this particular calculator requires some information, a little bit more information than some of the other calculators do. But let's say, for instance, we want to start with a Class A IP range, which is normally 8-bit, starting at 10.0.0.1. We're going to calculate that. That shows you first IP address you can use, which is the 10.0.0.1. This is your network address. This is where all of those devices live on that street. It shows you the range, your usable host range. A host, again, is a device that's plugged into the network. Goes from 10.0.0.1 all the way up to 10.255.255.254. And you say, well, why doesn't it go up to 255? Because the last IP address is used as the broadcast address. That's the one that's used. So if a device needs to shout out on that particular network, on that particular street, it uses the, in this case, it would be the 10.2, in this case, it would be the 10.255.255.255. It would then say, hey, hello, is anybody listening on this particular subnet, on this particular network, on this particular street? And there would be responses from devices that are listening. So again, and that's what it shows you down here. This is the broadcast address. This is the total number of hosts that you can have on that IP address range. That's a huge number. Of course, the usable hosts are only going to be this. It's -2 because you have one for the network address and one for the broadcast address. That's an important point to remember. When you go to take your tests, remember that the first address, which is usually 0, is going to be the network address. The last address, which is the 255, is going to be the broadcast address. 255 and 0 in this sense. Once we start breaking out the subnets, it changes a little bit. All right, this is of course your subnet mask. This is what that looks like in binary. So place value, we're going to go into here real quick. In binary, if you think of place value, it'll help get through the whole binary base 2 by the power of 2 system. So in binary, remember the numbers 1, 2, 4, 8, 16, 32, 64, 128. Those are what you have to remember for networking subnetting. In binary, of course, it just continues to go on, such as 256, 1024, etc., etc., etc. An easy way to remember all of that is you start at 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. And 64 times 2 is 128. We only need to go up to 128 in subnetting because all of those added together would be 255. That is the maximum number of IP addresses and bits available for an IP range. So each octet, that's a section of numbers before a point, contains 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. 8 columns within that section, that octet, as they call it. And instead of putting 8 columns before and doing the full 4 columns, really we're only going to be addressing 2 columns because the first column never changes. The first octet never changes. It's always 255 in the subnet mask. In other words, the first octet is always going to be dedicated to the network address. No matter what you do, the first octet is always dedicated to the network address. Then the second octet, depending on the class range, will determine if that octet is available or not. So a class B and a class C range, the second octet is not available. No matter what you do, those 2 octets are never available. And then in the Class C range, the 3rd octet is never available. It's always dedicated to network addresses. Only the last octet is available for hosts. So in a Class A, the first octet is always occupied, but that leaves the next 3 octets available for hosts, or for subnetting if you wanted to break those down into networks. And this is where subnetting gets kind of interesting. So we break out of the class and we go into classless subnetting. So a lot of industries, a lot of companies will always use the Class A private IP range, which is 10, in order to create their internal or private network. And they do so because it gives them so many options. They're not limited by how many network addresses and hosts are available. In this case, it's almost over 16 million hosts. That's huge. And if they had that many hosts, they could use it fully just as it is. In most cases, that's not the case. So what they do is they break it up. And you think, well, why would you need to break it up? Why not just use the classes and be good and done with it? Well, Class A gives you way too many hosts as it is. And you could do it. You could do it that way. You could set IP reservations in DHCP and say, okay, the servers are going to have IPs from 1 to 20, and computers are going to have it from there, type of thing. And you could do that. It's just it starts becoming a headache trying to sort things out that way. And then you could go, well, let's say I'm going to split up. And the reason you have network versus host IP ranges is because, as you've learned about VLANs and subnetting, you need to segregate your network. You need to segment it in order to provide some containers, some organization to your network, not only for organization purposes, but also for security purposes. So you're going to have devices on the network that you don't want having access to everything else. And you would have that with, if you just had a Class A IP range, and then you just separated and said, okay, servers are going to only have, I'm going to manually make sure that servers only have the first 20 IP addresses and computers have the next 50 or whatever. You could do that, but the problem is it's really hard to control security and to control different things on the network if you do it that way. Whereas if you segment and say, okay, servers are going to be on this network range. And when I say network, let me back up a little bit. Network, unfortunately, has multiple definitions. So network, the broad definition is a bunch of devices connected to each other, or more than one device connected to each other. It also means network address. And so when you say that these devices are on this network, it doesn't mean that at campus A, those devices. It's talking about at campus A, these specific devices are on this segment of the network. So that is a shorthand term for saying this segment of the network is dedicated to. So when they say network IP range, or this is the network portion of the IP range, they're saying that this is the segment of the network that's dedicated to specific devices, specific hosts. So what you'll do is you'll take, let's say, a Class A 10 private range, which is the 10 range, and you'll break it up and say, okay, we're going to take that, and instead of having over 16 million hosts, we're going to break it up to where it has multiple network segments to allow those hosts to be alive on those segments, to live on those segments in order to provide security, control, et cetera, on your network. And you break it up by going into the subnet mask. Again, the subnet mask is there to let the network device know that these particular hosts reside on this particular network segment. And so you specify the network segment by coming into the subnet mask. And a real easy example is to say, okay, let's say you have 50 servers. You do expect to get more. So you think, okay, let's make this fairly simple and do it a 24-bit subnet. That gives you 254 hosts, by the way. That's like way over what you need. And you can definitely adjust it accordingly. But one of the things you have to be aware of when you're creating these subnets is to go, okay, well, let's see, I've got 50 servers, and that's a lot of servers. Very seldom do you have that many, obviously, but this is a general example. Or let's say printers. Let's move over to printers. You have 50 printers. That's a more realistic example, because the servers will actually be on a different subnet that's much, much smaller. Let's say printers. You have 50 printers to start off with. As your company grows, it suddenly is 100 printers, because now we're talking a large number of employees and big buildings and different departments and so forth. And then if your company grows even more, and a lot of those employees need private printers so they can print off confidential information, your number of printers just went up to 200. So when you're designing these subnets, taking the server example, you're going to start, you're thinking, okay, small. But examine the type of device. Servers, probably won't go beyond a certain point. In fact, they'll probably get less. Whereas printers could get more or less. What's nice about this type of thing is in the subnetting is it can expand or shrink as needed. So printers, let's say you get more than 200, you're covered because you have an IP range, a subnet that's 254. So you would create that subnet by going in and marking in the subnet mask all of these values as true. And then that portion is for the host. So 3 octets are in use for networking. That gives you 254 host IP addresses. It also gives you a lot of network addresses, and you think, okay, why would I need so many network addresses? Side note, cool thing. So you have your 10 range, your whole 10 range. You can have multiple subnets. You can have different subnets. You can have a 17-bit subnet in one section. You can have a 24-bit subnet in another section. You can have a 20-bit subnet in another section, just depending on what you need. That range is so large, it allows you to do a whole lot of stuff. Now you have to pay attention to your neighbors. So if you're creating a subnet and you designate a section of the network to that subnet, so let's say you go, okay, I'm going to create the subnet of 10.2.30.whatever. That's going to be a 24-bit subnet, which is going to be 10.2.30.1 all the way up to 10.2.30, oops, excuse me, 10.2.30.254. Let's make that just like that. All right, so we've created a 24-bit subnet range. Let's say that's called 10.2.30.whatever, because it's the host. That's going to go from 10.2.30.1 all the way up to 10.2.30.254. But if we created a subnet of 10.2.31.x. Right, so let's say we have our 10.2.30.whatever IP range. It's a 24-bit subnet. It's going to give you the 10.2.30.1 all the way up to 10.2.30.254. But let's say we decided to create a 23-bit subnet range. That's going to be 10.2.31.whatever, which this is the default gateway, by the way. This is your network address. That's the beginning address. That's going to give you 10.2.31.1 all the way up to 10.2.32.254. So as you create your subnets, be aware that it does affect the IP addresses. It begins to take up more or less depending on the settings in the subnet mask. So, and by the way, a 23-bit subnet would look like that. So these are things to keep aware of, or to be aware of, to keep in mind as you develop subnets. Figure out how many hosts you have to support, how many networks you want it broken up into for, let's say, a campus or a location, etc. Kind of have that going into it, and then figure out how many hosts you have to support or possibly support, because you have to keep in mind future and is this going to be scalable? Can I grow easily? So I bring this example up because if you tried to do 10.2.32. Whatever, and you wanted this to be a 24-bit subnet mask, you think, okay, yeah, that's the next logical one. That's not going to work because you've already created a 23-bit subnet mask up there, and it's taken up 32 range. So you really have to be aware of your neighboring IP addresses. And a good way to do that, kind of a rule of thumb, is you think to yourself, okay, in order to, because you have thousands of network addresses, you don't have to stack them right on top of each other. So a good rule of thumb is to give yourself at least 5 IP ranges when you create a subnet. And what I mean is, so you create your first 24-bit subnet. That's going to host 254 hosts. You need to create another subnet. So one is for printers, let's say. The next one is going to be for computers. The next one is going to be for access points, and so on and so forth. And so what you want to do is go, okay, this one is going to start at 35. And this one is going to start at 40. And the next one is going to start at, let's say, 45 or 50 even, depending on the size of your network and how many hosts you have to support. Kind of give yourself a serious cushion. That way you don't have to worry about the expansion or whatever. Even if you waste those network addresses, you have thousands to choose from in this case, so don't worry about it. Obviously you don't want to be wasteful, but at the same time, really kind of plan out for expansion, contraction. So this is subnetting in general. This is a real basic concept or idea of subnetting, how to do it, etc. I would be happy to go into more detail with you if you have questions. All right, moving on from subnetting, we're going to go into IP address assignment, sections 5.1.6. So, static IP assignment, the good, the bad, and the ugly. You want to assign static IP addresses to certain devices on the network that you know are not going to change frequently, that aren't going to move around, or that need to be consistently contacted, such as a printer. It's a disposable item, and it gets replaced every so many years, but a printer needs to be constant on the network with an IP address. It can't be using DHCP due to, if you have a print server, it points to an IP address of the printer. And if that IP address is changing, then it's definitely more difficult or almost impossible for a print server to find that printer. And then you have the issue of, computers will lose connection with the printers and they'll have to go out and find the printer, and you just don't want that happening. So, and then network nodes such as switches and so forth, servers, they definitely need to have static IP addresses. The bad is where, with those addresses being assigned statically, a lot of times the devices do not connect back to DHCP, letting the server know that that IP address is in use. And so if a device has a static IP address, it's on a range that is in DHCP, it has a scope, and that device does not connect back to the DHCP server to let the server know that, hey, I have this address, the server won't know, and it could assign that address to somebody else. And so then you have an IP conflict, and you'll get reports of either computers or printers or whatever going offline. So that's the bad. So you definitely want to make sure that you put reservations in DHCP, or that you have a restricted range. So you have reservations and then restricted ranges, and in the restricted ranges it says make sure that the IP addresses between these points are not handed out to clients who contact you. So those are reserved, or restricted rather. And so then you can statically assign IP addresses within that range, and it doesn't matter if that device never talks back to the DHCP server. The ugly of statically assigning IP addresses, some people have had the great idea of making sure that all of their nodes on the network, including computers, have static IP addresses. They don't like to use DHCP. They say it's not as reliable, and it's just easier to know what the IP address is of a computer, so you can just directly connect to it. Heck, you don't even need DNS at that point. And so that works great if you've got maybe 2 computers, but have more than 20, even before then, but more than 20, and you're definitely going to have a serious headache of just trying to keep track of all of the devices and who needs an IP address, who belongs to what, etc. So that can be the ugly of statically assigning IP addresses. They briefly went over how the DHCP server works, how a device connects to the network, sends out a broadcast and says, hey, I'm looking for a DHCP server, I need an IP address. The DHCP server is listening and says, yes, I'm a DHCP server, here's an address, and you're good to go. You can communicate on the network. And then they keep that relationship going to where the device, after a certain period of time, because IP addresses, you can actually set the expiration date of an IP address, how long a device has it, and so that timer ticks down. And once it ticks down, that device says, okay, my time is up, goes back to the DHCP server and says, I need another IP address. And then the DHCP server says, okay, you're still on the network, here's an IP address. Oftentimes it's the same address. There's a renewal process that happens. If the device misses its renewal because it's been turned off, it's fallen asleep or whatever, in some way there's no network connection, the DHCP server, once that time ticks down on that particular IP address, it says, hello, are you out there? Okay, guess not. And then it pulls that IP and says, it puts it back in the available pool and will assign that to somebody else. Device starts up and says, yeah, I had this IP address. Oh, I guess I don't have an IP address anymore. And it goes through the process of releasing and renewing its IP address from the DHCP server. That brings up the point of too many DHCP servers. So if you bring a home router and plug it into the network, it has its own little DHCP server, and you could essentially have 2 DHCP servers on the network, where one is authentic and it's handing out proper IP addresses and the other is not. It's created an ad hoc network and it's handing out bogus IP addresses basically to clients, to hosts that are no longer able to connect to the main network. They're just a part of this little ad hoc network. The same thing can happen if you're setting up a new DHCP server, either virtually or physically. And as you're getting things all set up, plug it in, it's plugged into the network to receive updates and the whole bit. Get it all set up and think, okay, I've got just a few things left. Well, you don't realize that it's gone active. As you're setting it up, you're all right, let's make it active and, start configuring some of the ranges and so forth. It's on the network. And so when a device plugs in and says, hey, I need an IP address, that new DHCP server you're setting up says, hey, I'm here, I'll give you an IP address, which is probably going to be different than your other DHCP server. It's going to hand out different, IP addresses. So that is something to keep in mind. They talked about the EPIPA, how Windows will step in and assign an IP address to a device if it loses contact with the DHCP server, and how that is used to connect devices on a network, regardless if there's a DHCP server. If they've lost contact with the DHCP server, they're supposed to still be able to connect to each other. Really doesn't always work that way, and the devices need to know the other IP addresses of those devices, because there's no longer any reference as to who has what, especially as Windows just kind of randomly assigns an IP address. So A PIPA is really only there to show you, the network admin or the network tech, that, oh, there's an issue with the network, I need to figure out what's going on. And then be aware that old IP addresses can be retained. Again, if that device says, yeah, I still have such and such IP address, I don't need to contact the DHCP server, it doesn't know that that server is offline until a little bit later when it goes to renew itself and check in. It's like, whoa, DHCP server is offline. So if you have a device that has its IP address and it looks good, and a device that's pulling in a PIPA, don't assume that there's just something wrong with this device. It could be something wrong with the DHCP server, because even though this one device has it's retained its IP address, it's still not functioning properly. We'll go over the DHCP options and things. In the options, as you're setting up a DHCP scope, it's always important to set the options and to set available ranges, excluded ranges, reservations, etc. But then go into your server options and make sure that the DNS server, the domain name, and the default gateway or the router are specified. Some of the others are obvious, but if you don't specify the default gateway, you think, well, that's what the router is for. Well, if nobody knows how to get to the router, if nobody knows how to get to the default gateway, which is, you have your VLAN, your subnet, the network address is the default gateway. That's usually the .1 or whatever the first IP address is in that range. That's going to be the default gateway. And that's going to reside on the router, the core switch or the distribution switch that does that type of routing. And so unless devices know how to get to it, a lot of times that's not going to work. You need to make sure you specify the default gateway. And of course, pay attention to the IP ranges, the subnet masks, and the default gateways. Look for rogue DHCP devices. We talked about the home routers, virtual machines, the other DHCP servers, but also hotspots. Sometimes people will set up a hotspot and it broadcasts to other devices out there and they can begin to connect. So be aware of that. DNS, the domain name system, and a domain controller or DC are oftentimes paired up in the same server, even though they're two different services, because they handle similar things. It's a name resolution, it's device resolution. So oftentimes those two services are combined onto one server, just as a side note. So FQDN is something you'll hear frequently, especially as you advance more in the networking side of things, or even if you deal with putting computers on a domain and so forth, you're going to hear the FQDN, which is the fully qualified domain name. That's the whole domain name. So you have your computer name .mydomain.net. They talk about domain tree and domains, subdomains, all within zones, what those look like. Basically, a domain is a structure that allows computers to register in a system and to be controlled by policies. In a domain, you can have devices, you can have groups, you can have users, and all of those containers, it almost looks like the folder file tree, as they showed you. Those are all like OUs, as they call them, organizational units that allow you to specify different functions within the domain, what different things do, where they're housed, etc. The host file on a computer, it's kind of an old technology, but it still exists. So this is something you'll definitely need to be made aware of if you get into the security classes, that a Windows device will maintain a host file that specifies some of the default network connections. A hacker can potentially get in there and alter the host file and say, when somebody gets on the internet, send them to this server. And this server looks like Google. And in reality, it's their server and they're taking information from your computer and they can lead you into a whole bunch of nasty areas. So the host file is something to be made aware of. Also, people can get in and alter their own host file. So if you have somebody who's not connecting to the network, usually it requires an admin to alter a host file. So usually you'll see this on somebody's personal computer. If they're not able to connect to a network, let's say you have an open network, they're able to connect, but they just cannot get to specific pages. you might want to check their host file. Make sure that it has all of the defaults. Otherwise, it could be forwarding them to a wrong location. Then you have caching only DNS servers. The forward and reverse lookup, so you can look up a computer by its IP and get its name, or you can look up a computer by its name and get its IP address. Then you have the records, and these you'll definitely need to remember, at least some of them. The A record, which is the IPv4 or 32-bit addresses that are kept. The quad A, which is the IPv6. You don't often see those, but in a place that uses IPv6, you will see the quad A address. Then you'll have the PTR, but mostly the CNAME is what I want you to focus on too. That's aliases for hosts, just something to remember. You'll get questioned about a few of those. IPv6, brief history, too many too many devices for the number of addresses that IPv4 could supply, and so they had to create a new version of handing out IP addresses and something that was more robust. So they went to a base 16. That's by the power of 16. And if you think converting into binary is difficult, try converting into hexadecimal, where you have numbers and letters up to a certain letter. And you know, it looks like a MAC address is what it looks like, but it's an IP address. And yes, there are some very long addresses, but it gives almost endless possibilities as far as assigning IP addresses. So the future has been predicted for many, many years that eventually we will do away with IPv4 because it's just too old and too clunky, and it doesn't support enough, and we have to do subnetting and all that sort of thing. We're just going to move to IPv6. And they've tested out IPv6 many times, and it actually works fairly well. Really, all the devices now support IPv6, so if there was this giant mass move to IPv6, devices could support it. It would just require the network administrators to know that, okay, this is what we're moving to now, at least on the public domain. And then IPv6 hex shortcut, you'll want to remember, is that if there are multiple zeros between two octets, or not octets, but between two colons, they will just eliminate the zeros and have the colons next to each other. Tunneling. They mentioned tunneling and kind of glossed over it. And I had talked briefly about tunneling before when I was discussing private and public IP addresses. So tunneling is the process of, and I gave the example of campus A and campus B. You need to connect both of those campuses' internal networks to each other, so that way they can share information back and forth. To do so, you could run fiber between the two campuses, but that's kind of expensive. And if there's a fiber connection via the internet that's connecting the two, there is no need to run fiber when it's already been done for you. So the idea is to tap into the internet connection, the internet service provider connection, and connect the two campuses via a VPN or virtual private network, which requires tunneling through the network. And that tunneling means that, kind of as the description says, you are boring through the network. You are creating an isolated connection between you two that nobody else can see, or it would be very difficult for them to see. Basically, it's just how packets, as they're sent through the network, they're encapsulated. So picture a giant water pipe. It's the internet connection, and you need to connect the two campuses using that water pipe. You want your traffic to not be seen like all the other traffic just floating by. And so you encapsulate it in special capsules that sends that information to its destination, and that destination knows how to open up the packets. So basically, tunneling, again, is just creating a secure connection using the internet between 2 points. All right, IPv6 address assignment. So link local addresses are only valid on the current subnet. They use an FE80::: designation. They're non-routable because they're private, and so they require a NAT. They're not on the public address range. Just like IPv4 has their own private, so does IPv6. Then you have multicast packets that have the designation of FF00::. You will need to remember those, including the multicast packet, which is FF02::, and then your loopback address in IPv6 is ::1. So the loopback in IPv4 is 127.0.0.1. In IPv6, it's ::1. Multicast. So briefly touch on unicast, broadcast, and multicast. What that actually looks like. We've touched on it briefly before, but a unicast is a one-to-one relationship between, let's say, a server and a host. And that would be like walking into a terminal, airport terminal, or let's say Grand Central Station. Amidst all the people there, you spot your friend way across the way, and a unicast would be you walking through the crowd right up to your friend and having a conversation with your friend, just you two. It's a dedicated conversation. You can, and it can even be secure, and you go into a separate room and nobody else hears you. It's just between you two. A broadcast is you see your friend, same scenario, see your friend across the way in Grand Central Station. You pull out, this time instead of walking up to your friend, you pull out your bullhorn or your megaphone and call out, "Hey, John Smith, I see you over there." And it's up to John Smith to be listening, to hear you, and to respond. And hopefully, if there are other John Smiths in the area, they look your way and go, "Nope, I don't know that person," and they all walk away from you and ignore your conversation as you try to converse with John Smith across the Grand Central Station. Then multicasting is where you are speaking to multiple people. So you're in Grand Central Station and you see several of your friends out there and you need to talk to them. So instead of pulling out your bullhorn or your megaphone and calling out, "Hey, John, Susie, whoever, you don't want everybody else to hear you. You don't want snooping. And so you walk up to your group, you say, "Hey, let's go over here to a private room and we will all talk." And then you do so, and you talk to many, and they are all listening to you. And it's not just a one-to-one, you are talking to many at that point, but it is in a private location, in a private environment. That's multicasting. That prevents snooping. It also prevents traffic on the network, unneeded traffic on the network. So a good example of this would be if you have a deployment server which creates, you can create a master computer with an operating system, all the programs installed and everything, take a snapshot of that, and this is a rough example, put it onto a deployment server, and that server allows hosts to connect to it. It then creates clones. And so that deployment server will oftentimes use multicasting. You can also use unicasting, to where it sits there and it waits for a host to connect to it, and they have a dedicated connection to where that host then downloads the packets it needs and turns itself into a clone. Multicasting would be where you have, let's say, a classroom of computers that all need to be re-imaged with the most current version of Windows and all the software and stuff that are required for that class. And so you boot them all into the network. They call that PXE booting, PXE as a side note. And those clients talk to a server. That server creates that connection, and it's a multicast, where each one then is able to download from the server the files in order to all clone themselves. So that's another example of multicasting. Tools. Open up the command line. You can check IPConfig for basic network information on your computer. If you do the IPConfig/all, that does more information, gives you full information about your network connection. The IPConfig releases your IP address, it clears it, and then you do the renew, and it goes out to the DHCP server and gets a new IP address, or the same address. Basically, it's just forcing your device to reconnect with the DHCP server. And then if you find that you're having issues connecting to another device, another node on the network via its name, but you can connect to it via its IP address, one of the things to check first is your outdated DNS record. So if, let's say, you're remoting into a computer last week and that computer name changes, it ends up pulling the same IP address because the MAC address never changed, but its computer name changed, so DNS records are updated on the DNS server. Your computer comes back online next week, you need to remote into that computer again, but the name has changed. So you change the name on your remote software and you try to connect to it, but your computer is remembering that that device was named something else and has such and such IP address, there's an issue with its domain name registration. So if you flush the DNS, IPconfig/flush DNS, it clears your old DNS records and will go find new records. And then they use the IFCONFig in Linux. You open up a terminal and use the sudo command. As a side note, they mentioned the ETH0. So it's Ethernet 0. That's to designate a Ethernet connection on that device. Cisco uses that designation also for its various ports on the switch, and so it's just something to be aware of. And why are we talking about Linux when the world is primarily Microsoft and Windows? Linux, because as a network admin you need to be familiar with it due to many servers running on Linux. It's a lightweight server that does not require, huge amounts of patching, and it's oftentimes the best method for providing certain services. Also, Linux is the base operating system on Cisco and many other switches and routers out there, and so being familiar with Linux is definitely an important thing. But also, if you get into security, such as the Security Plus program, you'll have to know Linux, because Linux is oftentimes used for hacking or for checking the network for vulnerabilities. There are free versions of Linux, such as Ubuntu, which allow you to download an operating system. It has a slight graphical user interface, or GUI, and kind of looks like a mix of a tablet operating system and Mac. But it allows you, it's still primarily command prompt, but it's a free version of Linux, as is Kali Linux. Kali Linux, it's K-A-L-I, comes prepackaged with tools to check the security of your network and the devices on your network, etc. That's also used for hacking purposes. So be very careful at using those tools on your work network unless you're authorized to do so, or unless you have your own little segregated network that isn't going to cause any issues if you set off one of the network probes. All right, network communication troubleshooting. Start basic. Whenever you're troubleshooting a network issue, try multiple things. Check your connection, check your cable, check your IP address, check your connection to the network, starting close and working out. Use command line tools such as ping. Ping is like the submarine pinging underwater, or like a bat that pings in the air. It sends out a signal and it waits for a response. And so like a submarine that pings underwater, it sends out that echo signal and it waits for a bounce back to let them know what's out there. And same with a ping on a network, you send out specific packets to a specific host or node and you wait for a response. That device is supposed to respond unless that's been disabled. And in some cases, some networks, they disable that option. But if you're having issues connecting to a website via its name, try accessing it via its IP address, ping its IP address, ping other websites, ping other devices. It's kind of part of the network troubleshooting. Then you can also use IPconfig to check your network settings. Further command line tools, besides ping, are TRACERT, to where you can actually trace the route between your device and wherever the destination is that you want to go. And it lists how long it takes for that packet to get to those locations, giving you an idea that there's possibly a bottleneck someplace. There's a device that's overloaded, going bad, or something. And it uses the time to live. What is TTL? TTL is where a packet is given so many hops, or how many points it has to pass through before it expires. So they're all given an expiration period to where it can only be on the network so long. That way it doesn't just keep looking forever. It goes and then eventually dies. In some places it only lets, let's say, 10 hops before the packet dies. That's its time to live period. So keep an eye on that as well, because if the packet only has so many hops that it's allowed to do, then you may not be getting the information you need. On one hand, you're getting the information that there are so many hops that the packets are dying, so that's good information to know, but maybe something needs to be changed. The ARP, the Address Resolution Protocol, that's the table that lists MAC addresses and IP addresses. That's what DNS uses. And then they give you various commands that you can use to not only get that information, but also to return IP addresses in a specific list. You can delete ARP entries. You can manually add ARP entries. The other tool is NetStat. It can display a lot of information about your network connection. Again, just be aware some of these tools can be seen as a probe, so be aware of the policies on your network. Name resolution troubleshooting, just like network communication, you start small. Be aware of firewall issues. There are sometimes a firewall will block certain ports and certain policies, certain things from allowing certain things on the network. So such as a ping, it may be blocking the IGMP packets going through. So be aware of the firewall. Sometimes you have control over that, sometimes you don't. Again, you can use traceroute and NSLOOKUP instead of ping if the traffic is being blocked. And then documentation of the network is very helpful in a lot of instances where you're trying to get to specific devices such as switches or DC, etc. All right, that is the end of this lecture. If you have any more questions, please let me know. I know we briefly covered subnetting, which is a deep topic. I've included some YouTube videos that I hope are helpful. But again, if you have any questions, let me know.